Module 4.1, Introduction to Coarse Graining. In this module, we will learn about particle-based coarse graining techniques, theoretical foundations, what are the practical aspects of coarse graining and their applications. In this submodule, we learned about the fundamental principles, what is coarse graining, and how they are relevant for material design and mechanical engineering applications, understand its capabilities and limitations, and learn about few basic softwares that can be used for performing such calculations. As a schematic, I show you how a fully atomistic model is being coarse grained and to kind of simplify the simulation techniques. So as I mentioned, coarse graining is basically a way to simplify molecular systems by grouping atoms together. So if it's a methane molecule, you want to maybe represent that by a single bead, for example. And these models bridge the gap between microscopic molecular dynamics and macroscopic continuum models, and it enable efficient simulation of larger systems over longer timescales. These are heavily used for biological systems, such as understanding the biomolecular complexes like proteins and membranes, where details, atomic interactions are less critical than larger structure and functional properties. So mostly used in polymeric and macromolecular world. Material science applications, it helps us understand polymer and composite materials, drug design. Of course, it has limitations because we may oversimplify the interactions that might lose the definitely atomic level and as well as electronic level informations. Parametrization, we also learned about that in the previous module, that even developing classical force field for fully atomistic simulation is pretty difficult. So if you take a level up, then it adds another level of complexity and makes it very difficult to parameterize such models. And similar to the molecular dynamics models, force field models, they also suffer from transferability. So one particular coarse grain model may not be applicable for other. So it's very similar to molecular dynamics. The idea is to reduce the complexity by introducing pseudoparticles or beads. We still want to preserve the essential physics. We want to make different phase behavior, structural integrity, and dynamical behavior consistent. We want to achieve scalable accuracy, so we cannot compromise too much in accuracy. The good thing about coarse graining is it allows both bottom-up and top-down approach. So what I mean by this is, in bottom-up approach, you can derive coarse grain model from detailed atomistic simulations to ensure that the critical physical properties are retained. And in the top-down approach, it can simplify the system based on experimental observations and known properties, often used when atomistic data is scarce or not available. So it can kind of connect these different sort of models. And it usually is iteratively refined. So you might want to adjust the coarse grain model parameters through comparison with experimental data, as well as high fidelity theory data. So it's a kind of a bridge between such models. There are several advantages and disadvantages. So we talked about how it can increase the computational efficiency, especially for larger systems like proteins and viruses and so on. It can enable multi-scale modeling for larger systems. However, there are disadvantages such as loss of details, and that may lead to inaccuracy in your model predictions. Parameterization is extremely challenging and also limited transferability. So somehow we have to make a compromise between accuracy and efficiency, and it still remains a continuing development in the field of coarse grain modeling.